Stokes' law and terminal velocity. Very often in physics we're dealing with very complex situations, and the way an object moves through a fluid is one of these cases. Take for example a parachutist, or a boat moving through water. One way forward can be to make some simplifying assumptions, to develop a theory, then see how predictions based on this theory match experimental evidence, possibly adapting the theory as we go. The theory can sometimes give valuable insights into what is happening in more complex situations. Sir George Stokes investigated a simple case of objects moving through fluids. He investigated small spheres moving at low speeds. He took a sphere of radius r, falling through a liquid of viscosity eta. By marking out a known distance and timing the sphere to cover that known distance, we could work out the velocity of the sphere. So, making the simplifying assumption that we can ignore upthrust, the forces acting on the sphere will be its weight acting down and the viscous drag acting up. If the sphere moves with its terminal velocity, v sub t, the weight must be equal to the viscous drag. Don't forget this is ignoring upthrust. He found that the viscous drag was given by this term. This formula is provided on the datasheet. Stokes' law allows us to work out the units of the coefficient of viscosity eta. Here we have the Stokes' law expression again, and rearranging for eta we find that the coefficient of viscosity is equal to the force over 6 pi rv. The force will be in newtons, the radius in meters, and the velocity in meters per second. So, putting in the units into this expression, we get the units of eta will be newtons times seconds over meters times meters. This simplifies to newtons per square meter times seconds, but the newton per square meter is the Pascal, so we can give the units for the coefficient of viscosity as Pascal seconds. Stokes' law also allows us to work out the terminal velocity of a sphere. At terminal velocity the weight is equal to the viscous drag. The weight of the sphere is given by its mass multiplied by the gravitational field strength, and the mass is given by the density ρ multiplied by the volume 4/3 pi r cubed. The viscous drag we found was given by this expression, that came from Stokes' law, giving this, which we can rearrange and simplify. So the terminal velocity is equal to a constant multiplied by the radius of the sphere squared.